Video is going to cover section 1.2, problem solving with patterns. So here we have a couple of definitions. The first one is that a sequence is an ordered list of numbers. Let me go ahead and underline what we're looking at here. So a sequence is an ordered list of numbers. So for example, we could have something like 1, 3, 5, 7, and it just goes on and on and on, okay? A couple things to know about this is that it does go on forever, okay? And we can identify each term by using notation such as a sub 1, a sub 2, a sub 3, a sub 4, all the way to a sub n, where n would be considered our nth term. So in this section, what we're going to be doing is trying to come up with a pattern of sorts, or figuring out what the pattern is between these two numbers, similar to the first section of the book, and using that pattern to tell me what this nth term is going to be. Okay, this can be done by a list of numbers. It can be done using geometry. So we're going to go ahead and look at a few different things. Our next definition is something called a difference table. Okay, and this is what we're going to be using to find that pattern. So a difference table shows the differences between successive terms of the sequence. It's important to note that there can be more than one difference per table. I'm sorry, difference table per sequence. So let's go ahead and jump right into an example, okay, just so we can see what we're talking about. So let's go ahead and start with, let's see, okay, we'll start with a simple one. So let's say we have a sequence of 2, 5, 8, 11, and so forth, okay? So for this one, our difference table is going to be right here. So difference table is going to be how much it takes to get from one number to the next. So from 2 to 5, we have to add 3. From 5 to 8, we have to add 3. From 8 to 11, we have to add 3. And so the difference in this one is just going to be adding 3. Okay, so if I wanted to get the next one, let's say for instance, 11 plus 3 would be 14, and so forth. As far as terms go, this is our first term, this is our second term, 8 is our third term, 11 is our fourth term, 14 would be our fifth term. So that little number, the subscript, this one right here, tells us the term, okay, just like it is over here. All right. Okay, so in this specific example, we only had one difference. So that's what I mean by number of difference tables. We're going to do another one now that has more than one difference table. And I'm going to go ahead and just kind of put a line through here to mark the separation. So let's say we had something like, let me see, let's start with 5, 14, 27, 44, and let's say we're trying to find the next term, okay, dot, dot, dot. So for this one, I'm going to go ahead and start with the first difference table. So like over here, this was the first one. We only needed one for that one. So from 5 to 14, this is positive 9. Okay, there's 9 units to get from 5 to 14. From 14 to 27, that's going to be plus 13. Okay, so we're having to add 13 to 14 to get to 27. From 27 to 44, that is 17. Okay, so as you can see, these are not the same like they were over here. Okay, so these were all the same, which is why we could stop. These are not the same. So we're probably going to have to do another level of pattern. So let's go ahead and mark this first. So this right here This is our first difference, okay? This 9, 13, 17. We're going to have to do another one. So let's use a different color for that. And let's mark it down here. So second difference. So from this number to this number, what are we going by now? Okay, well, it looks like we're going to go up by 4. From 13 to 17, we're also going up by 4. So since we see that now these are the same, we can stop, okay, and we can kind of work backwards to figure out what this next number is going to be. So if I'm adding 4 to each of these, the next number I would also be adding 4 to. So 17 plus 4 is going to be 21, which means that in order for me to get to the next number from 44 to whatever this is, I need to add 21. So 44 plus 21 is 65. And this would be the next term in this particular sequence. If I wanted to keep going, let's say I wanted to figure out what the next number was, you would do the same thing. You would go ahead and say, well, I know I'm going to, from 21 to the next one, I'm going to add 4. So then this would be 25. So you're going to add 25 to 65 and so forth. Okay. So just to kind of recap, we have an ordered list of numbers. Okay, this is called a sequence. That's this up here. Each term is denoted by ace of 1, ace of 2, ace of 3, ace of 4, and so forth, all the way to ace of n, where that little number is the term. Okay, this is the number, kind of like the first one, second one, third one, fourth one, and so forth. Okay, if we figure out what the pattern is, we can identify subsequent terms. So to do that, we use something called a difference table. Okay. Sometimes a sequence will require more than one. So like this second example, we had to do 2 of them. Can it require 3? Yes, it can keep on going. So just be ready for that, okay? Because I believe one of your problems is going to ask you to do it about 3 times. All right, let's go ahead and move on to another example of problem solving with patterns. So here is a picture that involves tiles. This might look familiar to you from when you took Algebra 1. Back in that time, you guys used something called regression analysis to figure out what the formula was to give you the next square. So in the calculator, if you remember, I know it's been a while, but you kind of had like an X, Y thing. You would put all the X's, so you'd put the 1, the 2, 3, 4, 5, and the other one you would put those, so 1, 4, 9, 16. Actually, you wouldn't put the 5 because you don't have anything here. So you would just put it like that, and then you would do a series of buttons, menu, 6, well, I don't remember what it was, but something like that, okay? So what we're going to do here instead, because we're not using one of those calculators, and even if we did have one, we should not be using one of those calculators, is we're going to figure out the pattern from one to the next. So in this one, we're not going to use a difference table because you can kind of see it visually what's going on here. We have that with one square, let me switch that out. One square, we have one square. So 1 is still 1. With 2, we added squares on top. So it's a total of 4 squares. With 3 on the bottom, we're still layering up. So if you notice, we're just kind of, well, let me see if you can figure it out. Okay, so in this one we have 9. Okay, with 4, now it's a 4 by 4 square. So 4 by 4 is 16. With 5, now it's a 5 by 5 square. So we're multiplying this number times itself to give me the total number down here. So if I was trying to find for 6 squares, let's see, I would have to do 1, 2, 3, 4, 5, 6, and then up 6. So 1, 2, 3, 4, 5, 6. That's a horrible square, but it would look something like that. Okay, and yes, I could fill everything in, but all I really have to do is multiply 6 times 6 to give me 36 in the next sequence. So in the pattern here, we can see that to get the nth term, so this would be our nth term, okay, we are just multiplying n times itself, or to be more correct, we can say n squared. Because n squared, remember n squared is the same as n times n, which would be what we're doing here, 6 times 6, 5 times 5, 4 times 4, 3 times 3, and so forth. Okay? So in this case, we just had to kind of figure out the formula using a diagram. Will it always be this simple? Of course not. Sometimes you do have to do a little bit of work to figure out what that formula will be. Okay, it just depends on the situation. So let's go ahead and see what else we have here. I believe I want you to look at next Fibonacci numbers. So let's go ahead and look at the Fibonacci numbers. So there are some special sequences out there that we're going to look at now. One of them is the renowned Fibonacci. Now these numbers have a special pattern. I'm going to go ahead and start with the sequence so you can see. So the first one is 1, second one is also 1, the third one is 2, the fourth one is 3, the fifth term, so 1, 2, 3, 4. Yeah, the fifth term would be 5. Can you figure out the next term? I'm going to give you a few seconds, see if you can figure it out without cheating. Okay, so if you said 8, you are correct. This is a very special sequence. It has certain properties. Okay, so Fibonacci is defined by the following: f of 1, which would be this one right here, your first term. So in this, instead of using A, we're going to use F, just because Fibonacci is just that much more special. Okay, so f of 1 is equal to 1, always. F of 2 is also equal to 1, always. F of 3, well, I know it's equal to 2, but I don't want to use those numbers anymore. I'm going to actually use what I already have. So f of 3 is actually equal to f of 2 plus f of 1. In other words, it's this one plus this one. So this is the same as 1 plus 1, which gives me that 2 right there. Okay, using that same pattern, f of 4, which is now my 3. Let me get a different color here, just so we can kind of see the difference. So f of 4, not 3, f of 4, okay, is according to the pattern before. So based on this pattern, it should be the 2 before. So f of 3 plus f of 2. So let's see. F of 3 is 2. F of 2 is 1. So yeah, we're good to go so far. Let's check the last one that we have here. So f of 5, based on the previous patterns, it should be equal to the 2 before it. So that's going to be f of 4 plus f of 3. F of 4 is 3. And f of 3 is 2. 3 plus 2 is 5. So Fibonacci has the pattern that the nth term is actually equal to the 2 terms before it. So to write this a little bit nicer, because this is just specific examples, okay, we could say that f of n, actually, you know what? Let me give you a few seconds, see if you can figure it out. All right, so if we had an nth term here, okay, f of n would be equal to the term before it. So f of n minus 1. Okay, so let me show you what I mean here. So let's say n is over here somewhere. Okay, well, this would be the one right before it, right? So the one that goes right before it is n minus 1 plus the one before that. So f of n minus 2. Okay, And this only works after the third term because the first two terms are set in stone. So that's why we do have to include this condition here. And this is our formula for the Fibonacci sequence. Okay, something that you might want to look into. It actually has a lot of interesting history, so maybe some site work if you have some time. All right, let's look at another interesting sequences, I should say. We have, and you can find this one, by the way, on your in your book under the excursion exercises. These are polygonal numbers. You cannot say that. Polygonal numbers. And just like the word polygon implies, this does have to do with geometry. So for those of you who love geometry or just different shapes, this is a kind of a neat one. Okay. So the triangular numbers start with this sequence: 1, 3, 6, 10, 15. If you notice, they don't really have a specific pattern that you can see right away. So what I'm going to do with this one is I'm actually going to show you using triangles where these numbers come from. So starting with 1, if I put one dot, I have the number 1. There's only one dot. Okay. And this would be your first term. So this would be like ace of 1. Okay. Ace of 2 would be the number of dots required to make a triangle. So in the next part, to make a triangle, I'm going to need 3 dots. So ace of 2 is 3. Extending from this same triangle, okay, so I'm going to redraw that triangle here. I want to see what the next term is going to be. So ace of 3. So the third term, if I were to make it bigger, make the triangle even bigger, well, I would have to do this, right? So I need a dot here, and I need a dot right here. But this right here, this is not a triangle, so I have to create one. And now I have, let's see, 1, 2, 3, 4, 5, 6 dots. Therefore, we have 6 as our next triangular number. So the idea with this is that we're extending to the polygon by adding more triangles. And you can only have triangles because these are triangular numbers. If you keep on going, so let's say we're going to do one more. I'm not going to do the 15. That one takes too long. So we copy this one again. I'm going to bring it up just a little bit. Okay, so there's that first one. Think of it like putting toothpicks and marshmallows together, okay? And if I extend it one more time, so something like that. Now we have to kind of connect it this way. Otherwise, if this was a bridge, it would collapse, right? So now we have this one. This would be our fourth term. So ace of 4. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that would be our fourth term. And of course, you just keep going by adding more and more toothpicks and marshmallows, if you want to think of it that way. So this is what's called a triangular number, and it does have a formula. I'm not going to make you come up with it. I'm actually just going to give it to you. The formula for this is equal to n times n plus 1 divided by 2. So these are for the triangular numbers. Okay, so for example, if I were to ask you, let me make this a little bit smaller. So for example, if I were to ask you for the, let me see, the 10th triangular number, instead of having to construct this, for ace of 10, because that's gonna be a lot of toothpicks, okay? You can just plug it into the formula. So I could say 10 times 10 plus 1 divided by 2. So I'm just plugging it into this n right here, these two n's. So that would be 10 times 11 divided by 2. Let's see, 10 divided by 2 is 5. So the answer would be 55. So the 10th triangular number is equal to 55, which means that if I were to construct the triangles like I did up here, I would have 55 dots up there. Okay, so that's the idea of polygonal numbers. I'm going to go ahead and do a couple more just to kind of show you a little bit more geometry, because why not? Square numbers are a little bit easier to visualize. So for base of 1, which remember this is the first term, we always start with 1, so 1 dot. Okay, base of 2, well, now we want to construct a square with at least 2 dots on each end. So that's going to give us, that's a horrible square. That's going to give us 4 dots. So there's the next one. Base of 3, well, now we're going to extend the dots by 1 or more to give us that third term. But of course, this is not a square. So we actually have to make more lines to connect them. Okay, and that's a total of 9. Okay, base of 4 is going to be, well, the 4 across now. We start with our square, but again, we have to make this into a square as well. So I'm going to have to add some more toothpicks here and marshmallows. And you get the idea. Just going to pretend we did them all. And that would be 16. Okay, and so forth. So in this one, you should be able to figure out the pattern. It's kind of like the example we did before for the square numbers. All we have to do is square the number. So in other words, 1 square is 1, 2 square, so here look, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, and so forth. So if I asked you what is the 8th square number, you would just do 8 square equals 64. Okay. Last but not least, the pentagonal numbers. I hope I'm saying that right. This one I'm only going to do about 3 because they do get a little bit more difficult to draw. So first of all, a pentagon is the one that has the 5 points. Okay. So we're going to start with 1 because that's what we always start with these. So there's my 1 dot. Okay. And this is ace of 1. Ace of 2, we need to have at least a pentagon. So let's see, 1, 2, 3, 4, 5. All right, so this one has a total of 5 little dots connected by my toothpicks. Okay, ace of 3, here's where it's going to get a little bit interesting. We're going to extend this same pentagon. So I'm going to draw the first one. There's the original one with, the 5 points. And I'm going to use a different color just so you can see the extension here. Let's use this one. So from here, we need to extend this out. Let's see. And like I said, if you have like a grid or something, it'd be great because this one's actually kind of hard to draw. So I have to. Let me see. Give me a second. Let me concentrate a bit. All right, so here we go. So it looks kind of like this. If you think about it, you want to kind of line up these dots, okay? Mine's not too perfect. There is a better picture of this in your book if you want to reference that. But the point is, we're going to go ahead and count this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's where we get that 12 number. I'm not going to attempt to do the next one, but if we were to go on for the 22, you would go ahead and extend this again and then, do your pentagon. Okay. Let's get rid of all that though. But anyway, so you get the idea. This one does have a formula also, which I recommend to use definitely because as you can see, it's kind of a pain to be drawing these. But the formula for the pentagon one is, let's draw a little pentagon here, is equal to n times 3n minus 1 divided by 2. So this one I would definitely recommend using the formula instead of drawing them all because it takes a while, as you can see. So for example, if I were to ask you, I'm going to give you an example for this one. If I wanted you to find the, let's use a big number, the 12th pentagonal number, okay, well, this would take forever. We're not going to go all the way to ace of 12. No, it's too much work. So we're going to plug it in. So this would be 12 times 3 times 12 minus 1. Okay, just going to highlight the other parts here. Divided by 2. Okay. And this just becomes, arithmetic. So if I, distribute 3 times 12 would be 36. So this is going to be 12 times 36 minus 1 divided by 2. And that gives me, let's see, 12 divided by 2 is 6. 36 minus 1 is 35. 6 times 35, let's see, 6 times 5 is 30, carry the 3, 210. You can check my math. I kind of did it in my head real quick. But yeah, that's pretty much it. So this would be ace of 12 or the 12th term. Okay. I believe that's it for this lesson. Yep, that's it. So if you have any questions, go ahead and let me know. Hope you guys understood most of this.